The problem states, draw shear and moment diagrams for the beam. So the first thing we notice is that we have a triangular load here. And previously we've dealt with triangular loads. However, for shear and moment diagrams, where we need to find load as a function of x, we're going to need to do something a little more special compared to what we've previously been dealing with. So the first thing to notice here is that, like I mentioned, we need to find some sort of expression that will tell us how much load is applied as a function of x. So we can do that by using congruent triangles. So let's draw a smaller triangle. So this will be our red triangle. And then I will also draw a blue triangle. So drawing that blue triangle as well. So the base of the red triangle is, it has a magnitude of x, and the blue one has a magnitude of 9. So basically, this blue triangle is the entirety of this distributed load with a magnitude of 9 and a height here at 30 pounds per foot. So this is 30. And we drew this red triangle because that is our triangle at the point that we section. So if I section the beam here, then we would have a triangle like that. If I section the beam here, then we would have a triangle like that. So think of this as sort of a variable triangle, whereas the blue triangle here, the blue one is a fixed triangle. The red one varies as a function of x. So let's try to get the height h of this variable triangle here as a function of x. So if we simply use trigonometry, we have x over h is proportional to 9 over 30. And solving this, we get h is equal to 30 over 9 times x is what we get. This is super important because this h tells us the height of the triangle at a given section. So if I section here, then we know that this height is given by this function. So if this is 4.5, this is 4.5 foot distance from this location, then we would simply use this h equation to get the height of the triangle here as a function of x. Well, not a function of x, but so if I simply put in 30 over 9 times 4.5, then we know the height of this triangle in a numerical value. So that's what we want. I will demonstrate this shortly. Right now it might seem a little abstract, but you'll see in a very short period of time. Before I do that, however, I will be solving this equilibrium. So we know that the beam is in equilibrium, and we need to find sort of the reaction forces at points A and B so that we can actually solve the problem. So the force applying, we have a reaction force at A, and we'll just call this A. We have B, and we have a moment at point C, and that's a magnitude 180. We also have the distributed load, and during calculating shear and moment diagrams, we'll need to treat this as a distributed load, but for now, we can sort of treat it as a concentrated load in order to find magnitudes for A and B. So this is simply just the equilibrium. So this is yx, and we have the equation for the concentrated load as 1/2 times base times height, because this is a triangle, and we're simply getting the area under the curve. So we know that the base is 9, the height is 30, and 1/2 times this numerical value is equivalent to 135. So this has a magnitude 135. Solving this is pretty easy. We just need to do summation of forces in the y direction and summation of moments, let's say about point A. And this is, the convention is a counterclockwise moment is a positive moment. So doing summation of forces in the y direction really quick, we have A plus B. Let me actually use a different color for this. We have A plus B minus 135 equals 0. And for the moment, we're taking it about point A. So we have this distance, which is 2/3 of the way. So we know that a triangular load can be sort of converted into a concentrated load like this, where if L is our entire length, this is 2/3 L, and this is L over 3. So we already did that. So then our contribution from this load here, so it has a magnitude for the force, it has a magnitude 135, and the distance to the axis of rotation is 9 times 2 over 3, which is 6 feet. So this distance is 6 feet. And let's look at the sign. So we're going clockwise here, so that has a negative sign. So then this means we are doing negative 135 times 6 for the moment contribution for this force. And then let's do the moment contribution for this force. We simply know that B is a distance of 9 away from the axis of rotation. So then we have plus B, because this is a overall counterclockwise, so plus sign in front of it, B times 9. And then we have the moment itself, and that is a clockwise moment, so minus 180 equals 0. When we solve these two equations, these are pretty simple algebraic equations. For B, we get 110, and for A, we get 25 pounds. Now we can actually start sectioning the beam here. So let's determine sort of critical points on this beam. So the first critical point is when the load changes here. It's not like conventionally called the critical point, but I'm just calling it that right now to sort of show where we want to look at the beam. So first interval we want to look at it is x is 0 to 9, because we have a load here that doesn't change. And then we have this other section. So that would be x is from 9 to 13.5. So let's start off with x from 0 to 9, and let's section our beam there. So we have the left side of the beam like that, and then we're sectioning it. And here are the forces applying on this beam. First, we have our y and x. And let me just show x here, really. Actually, I'll use a different color for that. But we have a reaction force A that we calculated the magnitude of, and we have a distributed load, which we know the height of by this equation. And we also have our shear and moments at the point we section. And for our moment calculation, I will determine this red spot. Actually, let's make it yellow. This spot as O. So that will be our axis of rotation for our moment calculation. And we also have x that looks like this. So this is how our x is defined. So now we can solve the summation of forces and summation of moments for this expression here, or for this diagram. So we have the total summation of forces is equal to A, so that's simply A, minus, we have we need to find an expression for the contribution of this distributed load as a function of x. So that's like the whole point between the shear and moment diagrams. We're trying to see how the beam is sort of being affected by these loads. So what was the equation for the load for the triangle? It was 1/2 times base times height. So we know height because we calculated it here. We know base because it is simply x. X is this distance. It is the point from the very left side of the beam where A is up until the point that we section. So our base is x, and 1/2 is simply 1/2. So we go 1/2 times x times 30 over 9x, and that is our contribution from the distributed load. And we also have plus V1 here. So I'm actually going to change the color of this because yellow is not very good. Great. And then this is equal to 0. So when we solve this, we get V1 equals 30 over 18 x squared minus A. And when we rewrite this, we simply get 5 over 3 x squared minus 25. And that is our shear, or shear at this interval. So that's important. So now let's do the moment. So we have this total summation of moment about point O. We determined O as our axis of rotation due to its convenient location. So we get for this the contribution of A. So that is A. Let's see if it's clockwise, counterclockwise. That is indeed clockwise. So negative sign in front of A. So that's negative A times X. And then we have the contribution of this distributed load here. And we're going to temporarily treat this. So the thing is, even though it is a distributed load, for the moment calculation, you want to draw a force like this, and you want to see how far it is from our axis of rotation. This thing can get a little tricky, but with enough practice for these triangular dynamic loads, well, they're not dynamic loads, but for these triangular loads where we're trying to find something as a function of x, then it gets a little complicated. So make sure you practice these very thoroughly. So we have the sort of concentrated load for this distributed load, and it is a distance x over 3 away from our axis of rotation. We know this because for a triangular load, again, like I mentioned, if this is the concentrated load, it is 2/3 L, so 2/3 L, and also L over 3 distance for a given L here. So if this is our L, this is what we have. So that means we can use again the moment equation. So we know that a moment is force times distance to the axis of rotation. We know the force because we calculated in the shear force part of it. So our force is this for the distributed load. So we have, again, the counterclockwise positive sign. So that's plus 5 over 3 times x squared. This means that we have the force part of our equation done, and now simply multiplying this by x over 3, we have the overall term for the moment contribution of our distributed load. This is a lot to take in, but make sure you understand what's happening here. In addition to our force at A and also our distributed load, we have one more moment contribution, and that comes from M1. And M1 is a counterclockwise contribution. So we say plus M1 equals 0. And when we rewrite this, we get M1 equals minus 5 over 3 x cubed. Actually, that's going to be 5 over 9 x cubed. So that's 5 over 9 x cubed. Plus a times x. Our a is 25 times x. And we have the moment equation for this first interval. Now we will be sectioning the beam from 9 to 13.5 because that is what we have left. So instead of traditionally sectioning it from left to right, we will be sectioning it from right to left. So instead of doing this, we will be starting at point C, and we will be sectioning it like this. So sort of this area is where we cut the beam. For this, let me move this diagram a little bit to the right so we have space. So let's draw the forces on this. So we get the green color to show our forces. This is our V2, so our shear force number 2, and this is our sort of second moment, which is M2. This is our y-axis, and this is our L minus x. So notice how I use L minus x instead of x. This is pretty important. I think it was covered in either lecture or recitation, so make sure you understand why we're sectioning or why we're using L minus x for this arrow here. But anyway, we're sectioning from C to the right and doing our summation of forces and summation of moments. Let's again calculate this about point O, so MO for this interval. is starting with the summation of forces in the y direction, we have V2 plus nothing, because V2 is the only force, is equivalent to 0. So since we're in equilibrium, the total summation of forces is equal to 0, given that V2 is the only force and the total summation of forces is 0. We say that the shear force for this interval is equivalent to 0. This is important. So then we have the moment contribution, and we see that M2, so a clockwise moment exists. So negative M2 is equivalent to, there's one force or one moment I forgot to add. We have an 180 magnitude moment applying at point C, so that's 180. So in addition to this M2, we have a 180 pound per foot moment applying at point C, and we see that it is clockwise. So we say minus 180 is equivalent to 0. So solving this very simple algebraic equation, we say M2 is equivalent to negative 180 pounds per foot. All right, so on the right side of the screen, I've been adding our equations and information as we go along solving the problem. So now let's use that information to construct shear and moment diagrams for the beam. So these diagrams have, we have the shear here, and that is as a function of x. So this is our x-axis. And we also have the moment. So that is going to be the x-axis for the second graph, and the y-axis for the second graph. So that's moment with units pounds per foot. And our x-axis is going to be units of feet, and feet here as well. And our shear is going to be in the units of pounds. So now all we need to do is use these equations to sort of construct the diagram. In the previous video, I've gone over thoroughly on how to treat these as functions of x. So I will not be spending too much time on that. But simply put, we have for V1, the first part of it is a quadratic equation. And after we hit the second interval, so the second interval starts at 9 and ends at 13.5. When we hit the second interval, it'll be equivalent to 0. So let's see. At V1 equals 0, we have this expression here equivalent to negative 25. And at V1 equals 9, we have this expression equivalent to 110 pounds. So that's pretty important. So now let's check out the same for V2. Well, V2 is 0, so let's sketch our starting point for the shear diagram. So V0 is minus 25, so around here, that's minus 25. And we also have the maximum, or the termination point. So we have 110. We see that the sign for the x squared term is positive, and we know from algebra that a positive quadratic curve, or when a quadratic term has a positive sign in front of it, it's concave up. So then we can use that knowledge to sketch our function like this. So it's concave up like that, and at the point of termination for the quadratic, we're here, and once it hits 9, it is equivalent to 0 until the entire beam is completed. So from 9 to 135. So that is our complete shear diagram. Now let's do the same for the moment. We have M1 here. M1 is our first equation. And for M1, let's look at it at M1 at x equals 0. And we have for M1 0 plus 0, so M1 at 0, 0. This is a polynomial. So let's do the same for M1 at 9. So that gives us 5 over 9, 9 cubed, plus 25 times 9, equivalent to, and for this value we get equivalent to negative 180. So now let's do the same for M2. Well, M2 at 9 is obviously equal to 180, which is also equal to M2 at anywhere from 9 to 13.5. So we don't need to sort of write that down actually. So let's use this information to sketch our curve. So we have a change happening at x equals 9, and we also have the termination of the beam at 13.5. We're not going to worry too much about concavity for this polynomial. You actually don't need to worry that much about it for quadratics as well, but I mean, that's pretty easy to figure out whether it's concave up or down. But for this polynomial, we just need to show, so for the shear diagram, I would put a note that says this is quadratic. So this is quadratic. And for once we sketch out this polynomial, so it starts at 0 and we have negative 180 here. So it's negative 180. Goes sort of like this up until that point, and then at this location, then it becomes flat throughout, and then terminates at x equals 13.5. So again, this is pretty much it. The only thing I'd say, this is a polynomial, and this is pretty obvious that these regions are flat. So that concludes the whole shear diagram for this question, and also the moment diagram. And have a nice day.